Hi guys, so welcome to my channel. Today we are going to be talking about a design pattern that is widely used in distributed systems. Now, if you've been in software engineering for a period of time, you probably know what distributed systems are. Now, if you know what distributed systems are, then there's a chance that you know that there are certain design patterns that are commonly used when you are building a distributed system. And today we are talking about one of those design patterns, namely the circuit breaker pattern. Now, we are going to be looking at what the circuit breaker pattern is, what it does in the network, how it works, when we should use this pattern, and why we should use this pattern. So at the end of this video, you should be able to answer all these questions. So without further ado, let us dive into it. So what is the circuit breaker pattern? To define the circuit breaker pattern, we are first going to need to understand what a circuit breaker is. To understand what a circuit breaker is, we need to understand first, what is a circuit? So, I assume that you're watching this video from inside a house, and there's a big chance that as you're watching me now, you're in some sort of apartment or in some sort of office building. Now, that office has electricity, and there are light bulbs that are connected to a main grid in the office. Now, what is a circuit? A circuit is an interconnected network of components where some sort of current or power, or in the case of electrical circuits, yes, electricity, it flows from component to component. Now, there are different types of circuits. Even the road network in your city is a circuit because it connects different components, each component being an area or a borough or a town in your city to another town in your city or to another area in your city. So it is still thought of as a sort of network or as a sort of circuit. We are going to be talking about a computer network circuit in this context. And what is a circuit breaker? In terms of an electricity circuit, a circuit breaker is an electric device that is used to protect electrical circuits from surges, overloads, and short circuits. That is, if you have a circuit, there's a probability that at some point there is an overload, or at some point there is too much power inserted into that circuit, and the components connected to that circuit run the risks of being fried, or they run the risks of having too much power in them, and then some of their components get blown like a fuse. A circuit breaker guards against this in that once there is a malfunction in a circuit breaker opens that circuit and disables whatever is flowing through that circuit. Now, that is in the case of an electrical circuit. But in this case, we are looking at a computer network circuit such as the internet, right? Or maybe a private network hosted on a cloud provider for your own personal program, or a network of microservices or something like that. So that is what we are talking about in the context of our circuit today. Now, what is a circuit breaker in that context? A circuit breaker is a tool in a microservice based circuit or a network of computers. It is a tool used to disable the network or the system in the event that one of the components fails. Now, if you have a network of microservices, there's a chance that something could go wrong in one of the microservices. When something goes wrong in one of the microservices, that is where your circuit breaker comes into play. It is used to protect the network from being overloaded when a system in that network fails. And it is used extensively in distributed systems and distributed computing today. Assuming you have two services, service A and service B, right? We have what we call the request response cycle, and that is the cycle where service A sends a request to service B and service B sends a response to service A that says, hey, I have treated your request. Here is the appropriate response. Now, assuming service B fails, something goes wrong. One of the main thread in service B is occupied, or the database attached to service B fails. Now, if service A sends a request to service B, what then happens? Service A sends a request to service B and there is a failure response from service B. Now, this is in the case of an immediate failure, a failure that does not involve a timeout. This is in the case of an instant request and an instant response that, hey, your request has failed. Now, that is not much of a problem, right? That happens frequently in microservices. Anything could make a request fail, from a bad request or a bad request format, or even a service error, maybe on the internal workings of the service B that is receiving the request. That is the case of an immediate failure. Now, let us look at the timeout failure. A timeout failure, assuming service B has failed again, and now service A sends a request to service B. What happens in the case of service A sending the request to service B? Service A is kept waiting. Whatever the configuration for the timeout of service B is, or on the part of service A, after that timeout, the request is responded to with a timeout error. Now, assuming you have service A sending multiple requests to service B. Service A is a very popular service in your microservice, and service B is a service that service A depends heavily upon. So, as people are hitting service A, it spins up a new thread when there is a new request and it sends it to service B. That thread is kept waiting. Another person hits service A. It spins up another new thread and sends a request to service B. That thread is kept waiting. Assuming you have a limit of 3 threads on service A. Now, all 3 threads are kept waiting on service B for a response in a timeout failure. Now, assuming this happens, what are we looking at here? We can look at an overload on the part of service B, or we can look at some sort of denial of service on the part of service A, because now service A is fully occupied and it cannot attend to any more requests. So service A runs out of threads and now service A is down in itself. Now, assuming you have service B, it has waiting request 1, waiting request 2, waiting request 3. Even if service B comes back online, service B is going to be overloaded with requests and it will most likely break again from an overload. Now, you can see different scenarios where a timeout failure can cause issues for the dependent service and for the requesting service. Both services, in the event of a timeout failure, both services run different risks. The dependent service runs the risk of being overloaded when it comes back into service, and then the calling service runs the risk of going out of threads or out of processes that are available for it. This can lead to a poor performance. And you know, these days users have less and less patience for services. Users do not want to be waiting on a service that takes forever to do its job, or forever to perform a computation, or forever to return a response. So it is a very bad user experience. There is a type of failure we call cascading failures. A cascading failure happens when there is a service that fails. For instance, look at this interconnection of components. Service A, B, C, D, E, F. Now, assuming something happens on service E and its database fails. Now, service E database has failed, and following that, service E has failed because now it cannot retrieve data from its database, and now it can no longer serve requests. what happens? Immediately, service B and C will fail because they are requesting and they are dependent on service E. You can see that service B and C have failed, and what happens after that? Service A will fail because service A relies on service B and it relies on service C. So if it calls service B or it calls service C, the request will fail. You can see how that error is cascading through the entire network because now service F will also fail as it is reliant on service A. So this is what we call a cascading failure, a failure that is originating from one component in the network and it spreads throughout that network and causes other components to fail in turn. So that is something that we run a risk of in interconnected services. If one of the services fails, we run a risk of having other services that are reliant on that service and other services that are the entire service reliability tree will start to experience failures in turn, one after the other. So with cascading failures, a failure in one service or component could potentially lead to a total failure of the entire network, as services dependent on each other may start to fail if you do not have fault tolerance built into the network. What is fault tolerance? Fault tolerance simply refers to the rate at which a system can tolerate faults in it. I mean, the meaning is in the description. Fault tolerance, well, tolerance to faults. So it depends, or it speaks to how much your system can continue working and continue functioning normally even if there are faults in your system. Can your system continue to work as it should and provide the function that it's supposed to provide if it has errors? This is what fault tolerance talks about. So if your system does not have fault tolerance in it, you might start to have cascading failures and your entire system might fail if you have not thought about fault tolerance while you were building your system. Now, it is also a huge impact on your performance, right? Imagine you have a customer and your customer hits one of your failed services. Now, it's a timeout failure, right? So the customer waits for, say, 10 seconds before he gets an error response, hey, timeout, right? Now, you have retries in your program, right? So the customer does not even know, but your program has sent another request to the failing service. And that request fails after another 10 seconds. And your program sends another request to the failing service. And that request fails after another 10 seconds again. Now your customer has been waiting for a total of 30 seconds on a service that is never going to return a response. That is really, really bad performance because these days, like I said, customers and users have even smaller and smaller levels of patience for services. People want their data right away. People want their responses right away. So it is very critical that there are different patterns that are used to ensure that users get responses right away in terms of asynchronous programming, using message brokers to make sure that, hey, once a user performs an action, they get a response right away. Even if it's a huge computation, they get the response right away while maybe like a worker thread starts to perform the computation in the background. So you do not want to keep customers waiting. You do not want to keep users waiting. But now your user is waiting for 30 seconds on a service that will never return a response. That is really, really bad performance. And it could lead to a loss of confidence in your program. It could lead to your customers running to a competitor. It could lead to people dumping your program. And it could lead you to, even revenue loss. If your program is taking, if your program has bad user experience and it's taking too long to respond, you start to lose revenue to your competitors. Now, how do we solve this problem? A circuit breaker is a way to solve the problem. It's not the only way, but it is the way we are talking about today. Now, a circuit breaker works by having a proxy program sitting in front of a high traffic service. If it's a very popular service, you have a proxy sitting in front of it that is monitoring the health of the service and is monitoring the different parameters in the service, like the amount of time it takes for the service to respond to requests, the error rate of the service, and things like that. Now, when a request hits the service, your proxy program that is acting as the circuit breaker, that proxy program monitors the request and sees the status of the response and the time it takes for the request to be served. Now, it monitors the response status, the response time, the success to failure ratio of the requests, that is how many requests are succeeding versus how many requests are failing, and it also monitors the health of the service by regularly sending a ping to the service and checking for the response to that ping to see that, okay, this service is healthy or this service is still serving requests. Now, if you have two services, service A and service B, and now in the middle of that you have a circuit breaker, what happens? Service A still sends a request to service B, but this time service A sends a request through the circuit breaker to service B, and service B sends a response back to service A through the circuit breaker. So the circuit breaker sees the entire request response cycle, and the circuit breaker can tell that this request was well served and was successful, or this request failed, or it took 220 milliseconds to serve this request, different metrics like that. Now, assuming service B fails again, service A sends a request to service B and the request goes through, but now service B sends a response that is a failed response back to service A through the circuit breaker. Now, the circuit breaker is going to record that error, and it is in the internal workings of the circuit breaker, it is going to record that error and increment the number of errors that have been recorded, or whatever mechanism the circuit breaker is using internally to monitor the error rate. Then it will send the error back to service A. So what happens if that error rate reaches a specified threshold? Maybe the error rate is now 70% of the requests are having an error response, or 80% of the requests are having an error response, or 50% of the requests are having an error response, depending on the configuration of the circuit breaker. What happens when that happens? Now, you see the circuit breaker trips into an open state, and then it refuses to pass along any request to service B anymore. So when service A sends a request to the circuit breaker just responds to service A with an error response or a default response, or in some circuit breakers, it sends a cached response that has been cached from one of the previous requests, right? So that it will just send some form of data as a fallback instead of sending a request to service B that will most likely fail. Now, this is how a circuit breaker works in theory, and this is how it also handles the states when there are failing services on the downstream part of the circuit breaker. Now, this action will help the request to fail fast. So your user hits that endpoint, or your user hits that service, and it gets an immediate request. Even if it's an error request, an error response, it is fine as long as it's getting an immediate response and is not kept waiting. So the request fails fast, and then the thread that made that request, the thread that was used to send that request, is free to handle another request. So service A is not going to run out of threads because threads are waiting on service B, and service B is also not going to be overloaded by requests when it becomes healthy again. So you can see how the circuit breaker helps us to mitigate against the two risks that we discussed earlier, right? So that is how the circuit breaker works. Now, why is the circuit breaker tripping necessary? It's necessary because now the requests will fail fast. There is no longer any period of waiting. We are no longer waiting for a failed service, and then our threads are free to be used again. Now, the user is not going to be kept waiting. Requests are not queued up waiting for the failed service, right? Threads are not going to be queued up waiting for the failed service in the event that the service becomes LD again and it becomes overloaded by requests. Now, server threads and processes are also not kept waiting, so resources are free. And we can return a default or a cached value as a response instead of errors. Now, a circuit breaker has three states. It has the closed state, it has the open state, and it has the half open state. The closed state is the state where the circuit breaker is normally, where a request comes and the circuit breaker passes that request on to the downstream service and waits for a response and passes that response up to the upstream service. That is when the circuit breaker is closed. But when you hit a failure threshold, right? When you hit a failure threshold, the circuit breaker will go into the open state. Now, the open state is a state where the circuit breaker is not going to allow requests to go through because the service on the downstream end of the circuit breaker is failing. So in this open state, the circuit breaker will be returning cached values or default responses or error responses to the upstream service. Now, when the circuit breaker goes into the open state, it triggers a timeout that begins to read for a set number of seconds or a set number of milliseconds. Now, you can use a circuit breaker. Or you have a service that takes time to start up or reboot after a failure. You use a circuit breaker to ensure that that kind of service has enough time to start up or to reboot on the event that the service experiences a failure. Now, if you have a service with time-consuming operations or a long timeout, that kind of service is risky because users will think their operations are being run, or they will think that their request is being served and they will just be waiting. Meanwhile, the service is failing. So if you have a service that has time-consuming operations that people might have to wait for, and you are not using like service workers to carry out the operation in the background, it is advisable you have a circuit breaker in front of that kind of service so that if the service is failing, people will not be waiting thinking that their service is being, or their request is being run. For instance, you have a service that compresses a video or compresses a picture or uploads a video or things like that. People will think that their video is being uploaded or that their picture is being compressed. Meanwhile, the service is just waiting for a timeout. So it is advisable that you do not make people have false expectations like that, and you return an error to them immediately, letting them know that, okay, your response has failed and we are not carrying out your operation. Same thing if you have a service with resource intensive operations. You want to use a circuit breaker to make sure that there are no tasks queued up for that service in the event that the service becomes LD again. Because if the service becomes LD again, now you have resource operation upon resource operation upon resource operation. For instance, like an IO operation, you have operation on operation on operation, and it could lead to some sort of almost like a denial of service, like I said. So now your service is not free to handle any requests. So you want a circuit breaker in front of that so that if the service is not healthy, it does not queue up requests for that service and requests just bounce back and fail. Now, you also use a circuit breaker if you want to give a service time to scale up in the event of a traffic surge. For instance, you have a service that is really popular at some peak hours of the day, maybe like a service for uploading pictures, and hey, people are really uploading pictures when they are on their way home from work. Now, at that peak hour, that service needs to scale up. So if the service, during the time the service is scaling up, you want a circuit breaker in front of that service so that the service can have enough time to do what it needs to do before it starts to accept requests again. What are the advantages of a circuit breaker? It helps requests to fail fast, and it prevents delayed responses to requests. It can be used to return default values or cached values as a response when a service fails. Now, the issue of failing fast is something that I have already explained. It helps your services to fail fast in the area that people are not kept waiting for a service that is going to fail, and responses to services are not going to be delayed, right? So if there's a service that is failing, the request will fail immediately because the circuit breaker is just going to respond to the request immediately. Now, it can also be used to return default values instead of error values from the failed service. It can return default values like try again later, or it can return a cached value. If it is a request that has been made before, it can return a cached value back to the calling service, right? Now, that brings up the issue of how recent the data in the cache is, but that is another issue entirely. But the core idea is that you can return cached values back to the calling service. Now, you can use it to provide graceful degradation so that you do not have cascading failures in your network. You use it to provide graceful degradation in that the error is gracefully handled in the service and you do not have errors propagating through service after service. So you can use it to provide graceful degradation of a service through fallbacks, like we said, either through a default value or through a cached value. You use it to enhance the fault tolerance of a network by isolating and managing failures within the network. That is what a circuit breaker does. And it can be used to enhance user experience and program performance, as requests are not timing out on broken services. So like we said earlier, the user experience will be better because the user does not have to keep waiting and waiting for a failed service. And the program will perform better because now there is a very little time that the request has to wait before it gets a response, as opposed to it waiting for a timeout. And it also reduces the CPU overhead, as threads are quickly freed up and the calling service does not have to use all its threads that are kept waiting on the downstream service. So quickly the threads are freed up and the upstream service can reuse that thread to serve another request. What are the disadvantages of this pattern? It brings added complexity to our networks and programs because now we have to add another component just to work as a circuit breaker. So it's added complexity, there are added resources that we have to dedicate to the circuit breaker, added CPU, added computing, and sometimes we might not need that in our system if the system is not going to handle, like for instance, a large amount of traffic. It might not be necessary, right? So that is one disadvantage of this pattern. Then, if the parameters like the failure percentage or threshold and timeout are not properly tuned, it could lead to too many requests being rejected or blocked, or the circuit breaker might not reject any request at all. So what does this mean? If the timeout is not properly tuned or the failure percentage is not properly tuned, it could make too many requests get rejected because now the circuit breaker is not going to function as it's supposed to be, and it's going to trip into the open state too early, or it's going to trip into the open state too late. And then if it trips into the open state too early, requests that are supposed to be served will not get served. They will just get the circuit breaker response. Or if it trips into the open state too late, requests that are supposed to be handled by the circuit breaker will still make it down to the downstream service, and then we are not getting the benefit of the circuit breaker at all, even with the added overhead of the circuit breaker. Now, it introduces additional overhead as resources have to be dedicated to the circuit breaker program. We already discussed this. Now, when you have a circuit breaker, you have additional CPU resources that need to be dedicated to the circuit breaker. You have additional, additional tooling, additional tuning of parameters, additional tools and packages to install on our programs and things like that. So it's at an additional cost for us to include a circuit breaker in our program. And also, circuit breakers, when they are not properly tuned, they may trip as a result of false positives, right? Now, there are some times that a service might reject the request, or there is a row of requests that they all get rejected in succession because they are either badly formed, or they are malformatted, or the requests are actually meant to be rejected by the service. But the circuit breaker would think the requests are being rejected by the service because the service is on LD. Meanwhile, the requests are probably just badly formed, or the requests are probably not supposed to be, they are not in the proper format or in the proper pattern or something like that, and the service is rejecting them. So this can be seen as a false positive by the circuit breaker, and it may cause the circuit breaker to trip even though the downstream service is LD. So that is a risk you run with a circuit breaker. If there are too many requests being rejected by the service, even if the requests are malformed or are malformed or something like that, if too many requests are rejected, the circuit breaker might trip even though the service is still LD. And then requests that are meant to be served by that service will be rejected by the circuit breaker, even though the service is still very, very healthy. Now, this is how the circuit breaker works in pseudocode. If you have a request, if the request has an error response, now increment the error response counter of the circuit breaker. If the error response counter is equal to the error response threshold, or has exited the error response threshold, open the circuit and initiate a timeout. Now, when we have that timeout, the timeout has elapsed, go into the half open state. Now, if a request comes in the half open state, if the request has an error again, go back into the open state and initiate a timeout. Or if the request is well served and a specified number of requests are successful, go back into the closed state. So this is how a circuit breaker works in pseudocode. So you understand the mechanics behind the circuit breaker. So basically, it is not too much. We can code our own circuit breakers, but it is probably best if you use a well-tested service or a well-tested package for your circuit breakers. Now, this is an example of using Oposum. We import Oposum, the circuit breaker, and we import Axios from Axios. Now, we define our function to fetch the external data. It's an asynchronous function. Now, we make our Axios request in that function. To use a circuit breaker, you wrap the function that is making the call to the downstream service, you wrap it in the circuit breaker. So you say, okay, constant breaker is a new circuit breaker. You pass it the function and you pass it a configuration object. Say the timeout is 3000 milliseconds, the error threshold percentage is 50%, and the reset timeout is 5000 milliseconds. That is the time before it goes into the half open state. Then you use the circuit breaker, you fire it, and it sends that request down to the downstream service. So this is basically how a circuit breaker works in essence. So we have been able to look at some things today. Now you've been able to learn how a circuit breaker works, and how a circuit breaker handles requests, and how a circuit breaker trips into the open state. If you have any questions regarding the circuit breaker, please feel free to leave it in the comments. And if you have any ideas on any videos you'd like me to make on any particular design patterns for either software engineering or system design, please feel free to leave it in the comments below. If you have enjoyed this video, like and subscribe so that we can keep making videos for you, and I'll see you at another time.